All right, for the examples that we have in the Riemann Sums notes, we can sometimes use a calculator for these problems, sometimes not. If this is problem number 3, that tells me it was non-calc because it's 1 and 2 that are calculators. So I'll try to do this without a calculator, see how it goes. The rate of fuel consumption in gallons per minute recorded during an airplane flight is given by a twice differentiable and strictly increasing function r of time t. So they tell us r is gallons per minute. It's a rate. The graph of r and a table of selected values for r of t for the time interval 0 to 90 minutes are shown above. So part A says use the data from the table to find an approximation for r prime of 45. Show your computations that lead your answer, indicate units of measure. So for part A, we are trying to approximate a derivative. And if we're using a table to do that, we're going to find an average rate of change with numbers that surround 45. So 45 is not in here, but 45 falls between 40 and 50. So I'm going to use these 2 points to find my average rate of change. So it would be r of 50 minus r of 40 over 50 minus 40. And that is 55 minus 40 over 10. This is 15 over 10, so 1.5. Now, what about the label? So even though this says r prime, remember r is already a rate of change. So this is gallons per minute, or you could say gallons per minute squared. So think of this as like r prime is really like a second derivative. All right, and part B, the rate of fuel consumption is increasing fastest at time 45 minutes. What is the value of r double prime of 45? Explain your reasoning. So let's take a look at the graph here too. So at 45, they're telling me the rate of fuel consumption, now that's r itself, it's increasing the fastest. So that means you have the steepest slope right there. What else does that mean, increasing the fastest? This is also a point of inflection, right? See how the graph is going from concave up to concave down right there? It does switch again to concave up. But right here, we are, r is increasing the fastest because these steeps are getting steeper. These slopes are getting steeper and steeper and steeper. And then it finally hits sort of like a high point and tapers off. What does that mean about the second derivative? So if this is a point of inflection, then the second derivative needs to be 0. And it's 0 rather than undefined because this does say that r is a twice differentiable function. That means that it exists for all of these t values, for r prime and r double prime. Okay, so what am I going to write? I want to say this is a point of inflection. So r of 45 is a point of inflection. Since r of t is twice differentiable, r double prime of 45 equals 0. The options were 0 or undefined because that's what the second derivative is at a point of inflection. And so I know it has to be 0 because we have a twice differentiable function. Okay, part C. Approximate the value of the integral from 0 to 90 of r of t dt using a left Riemann sum with 5 subintervals indicated by the data in the table. So they're not equal subintervals. Is this numerical approximation less than the actual value? Explain. All right, so let's do part C. First off, we're trying to approximate this integral, so I just like to write this down. dt is approximately equal to, so we're using subintervals dictated by the table. So that just means, see where we have points here? The first subinterval has a width of 30. The next one is only 40. Let me get my extra marks off of here. The next one is at 50. So the next one is only, so we went from 30 to 10 to 10 to 20 and 20 again. And did it say left or right? It said left Riemann sum. So take the point on the left of each interval and make a little rectangle out of that. I can see visually that this approximation will be less than the actual because there's some missing space, right? If I didn't have a graph to look at, they did tell me that R is strictly increasing. So because R is strictly increasing, if you do a left Riemann sum on an increasing function, the rectangles will always be sitting underneath the function. And you can always, if you don't know what it looks like, I just show myself an increasing function and I start, doing a left sum and I realize like, oh yeah, okay, I'm missing space. Anyway, so the first one is 30 times 20. We can just show our work for this, I think. 30 times 20 plus the next interval is 10 times 30. Plus third rectangle is 10 times 40. Plus this is 20 times 60. Oh wait, no. I should use the table, shouldn't I? I should make sure those are right. 20, yes. 30, yes. 40, yes. Okay, 55. This one's not quite 60. So that was 20 times 55. Last rectangle has a width of 20. And we're at 70, which was 65. Now remember, you don't have to simplify this answer. I'm going to, but you don't, because it feels weird not to. You would still need to label this, and we still have to answer other questions. So approximate the value. So I did this. What is this measured in? If you integrate gallons per minute, it means what you're doing is think about the area of all of these. We just did gallons per minute times minutes. That's going to leave me with just gallons. So whatever this is, it is that many gallons. Is this approximation less than? Explain your reasoning. So I would say R of t is strictly increasing. So this approximation is less than the actual integral from 0 to 90 of R of t dt. Remember to always write your dt or dx or whatever the scenario is. I said I was going to calculate this, but no, I'm not, because I won't have time. And again, you're trying to save time too on your AP test. Okay, let's see. For 0 to 90, explain the meaning of the integral from 0 to b in terms of fuel consumption for the plane. Explain the meaning of 1 over b from 0 to b of R of t dt in terms of fuel consumption for the plane. Indicate units of measure in both answers. So I kind of did the first part in part C by labeling this. When I integrate, when I do the integral of R of t dt, this just comes out to gallons because it's like gallons per minute times minutes. If you add a bunch of these areas of rectangles together, you're left with gallons. What's this one? If you're left with gallons, but then you turn around and divide it by b, b is the distance from 0 to whatever, wherever we're stopping. That's divided by minutes again, like b minutes. So this is telling you a rate again. This is giving you, this is our formula for an average. It's like our average R. And remember, R is measured in gallons per minute. It's like our average value. You're adding up all of the R of t's and dividing by how many minutes we looked at. Okay, so let's put that into translation. The integral from 0 to b of R of t dt, remember this will give me gallons, so is the number of gallons is the total number of gallons used. What is this? Consumed? Yeah, consumed. How about I just say from 0 to B minutes? You could say in the first B minutes, whatever. And then the 1 over B times the integral of from 0 to from 0 to B, excuse me, of R of t dt is the average rate of fuel consumption, because remember the average rate of the rate of fuel consumption is R of t. It's the average R. So it's the average rate of fuel consumption from 0 to B minutes. All right. This is just a formula to have memorized, by the way. So that's why I'm saying the word average. It's not like an average rate of change. It's the average R of t. What else did I have to do? Oh, indicate units of measure in both answers. Total number of gallons, did that. Average rate of fuel consumption in gallons per minute from 0 to B minutes. Okay, did I answer everything? It's always good to double check that. Did you answer everything? Explain the meaning of this, explain the meaning of this, indicate units of measure. Okay, done. Second problem. We have another graph. This one's not strictly increasing. We have points on the table again. So here we have the graph of the velocity, v of t in feet per second, of a car traveling on a straight road for 50 seconds is shown below. A table of values for v of t at 5-second intervals is shown to the right. During what intervals of time is the acceleration of the car positive? Give a reason. Sometimes I give a reason before I get the answer. I just think this helps straighten it out in my brain. So when would the acceleration be positive? So acceleration would be positive. A of t is greater than 0 when I have a velocity graph. So how does that correspond to velocity? Acceleration is the derivative of velocity. So if the derivative is positive, the function is increasing. So anytime velocity is increasing, a of t is greater than 0. This occurs on what intervals? Let's see, we're increasing from 0 all the way to 35. And then again, this little 40, excuse me, this little 45 to 50 section. So I'm going to use interval notation for that. What did I just say? 0 to 35, yep, and 45 to 50. So I already gave my reason first. I answered it. Should be good for part B, or part A. Part B, find the average acceleration of the car in feet per second over this interval. So average acceleration. Now, remember, normally if I have an f of x graph, a position function, I would say find the average velocity, and you would say, oh, that's change in y over change in x. This is the same thing. The average acceleration is the change in velocity y over x. So average acceleration is v of 50 minus v of 0 over 50 minus 0. I'm treating this non-calculator again, so v of 50 is 72 minus v of 0 is 0 over 50. I could leave it as 72 over 50, but that bothers me. I'm going to divide it, so 36 over 25. And what would the label be on this? So this is an acceleration, remember? So you just did change in velocity over change in time. So that is feet per second squared. Find it. It didn't ask me to explain. Okay, part C. Find one approximation for the acceleration of the car at t equals 40. Show the computations. So they want me to find a of 40. And if I could make that equal to v prime of 40, then I would. But I have to approximate this because I don't have a velocity equation to type into. So what is surrounding 40? We actually have 40 for the velocity. So what we should do is find the slope either between 40 and 45, or do the slope between 35 and 40. They're both negative. Or I could do the slope, I think I could do the slope from 35 to 45, but I think it would probably be best to use one of the fives. So I'm gonna go 45 to 40. So I'm gonna say that's v of 45 minus v of 40 over 45 minus 40. I think that there would be several answers that were acceptable to this one. So what was v of 45? 60 minus 75 over 5. That's negative 15 over 5. So I'm getting negative 15 over 5. So negative 3. Again, this is an acceleration, so feet per second squared. If you went from 35 to 40, you'd get a slightly different answer. If you did 35 to 45, different answer. So I think any three of those would be acceptable. All right, and then part D. Approximate this integral with a Riemann sum using midpoints of 5 subintervals of equal length. Use correct units and explain the meaning of this integral. All right, so we're going from, should really be changing t, shouldn't it? What is the width of each rectangle going to be? So 50 minus 0 divided by 5 equal subintervals is 10. So on this graph, I want to mark this off every 10 units. So I like to, if I have a graph, I like to use it, put the visual in. Now this is the annoying part though, right? You have a hybrid AP test, so you can't just like draw on your computer screen, but you could sketch on your paper. We want midpoints for each subinterval. So that means that the height of the rectangle has to go through the center of each of these. So the heights I'm using are at 5, 15, 25, 35, 45. And you can see, especially with midpoints and a function that's not always increasing, sometimes the rectangle is outside of the function and sometimes it's inside. So that's kind of interesting. Okay. So this is about equal to, they're all going to have a 10 times something. So 10 times, and now I'm just adding the heights of the rectangles. So what did I say? At 5, I want to circle them here. 5, 15, 25. I just don't want to use the wrong number. All right, so 12, 30, 70. And 81, 60. I'm not actually going to do the math on this. If I don't have a calculator, I don't have to simplify stuff. I'm getting points for showing this work in my label and my approximation. So what would this be? We just took the area of these rectangles. So it was feet per second times seconds. That's going to leave you with total feet. So the label on this is feet. And what is my interpretation? So the integral from 0 to 50 of v of t dt is the total, let's see, what is this thing? Car. The total distance the car traveled. The car traveled in feet from 0 to 50 minutes. I am saying total because all of these were positive. If I had any negatives in here, then I would say, instead of total, I would say like the net distance or something like that. Or the net change in position, something like that. Okay, let's look at 5. Is this our last one? Oh no, 5 and 6. Okay, so 5. Here's another table, no graph this time. The rate at which water flows out of a pipe is given by, it's got cut off, R of t. Differentiable function. The table shows the rate as measured every 3 hours for a 24-hour period. Use a midpoint Riemann sum with 4 subdivisions of equal length to approximate this. Use correct units. Explain the meaning. All right, we're going from 0 to 24. R of t dt. What is delta t? It's 24 minus 0 divided by 4 subdivisions of equal length. That means we're doing a width of 6. So the first rectangle goes from 0 to 6. The next one goes from 6 to 12, 12 to 18, 18 to 24. That's 4 rectangles. We're using a midpoint Riemann sum. So I'm using the middle values of each of those intervals. So 3, 9, 15, and 21 are the times. So this is about equal to, every rectangle has a width of 6. And then I can just put in the numbers. 10.4 plus 11.2 plus 11.3 plus 10.2. What would the label be on this? We just took gallons per hour and multiplied by hours for every rectangle. So this would leave me with gallons. And what's my interpretation? So this integral is the total number of gallons. What's happening? Water's flowing out of a pipe. Total number of gallons that flowed from the pipe in 24 hours. From 0 to 24. Okay, part B. Is there some time between 0 and 24 such that r prime of t equals 0? Justify your answer. The question is this MVT, mean value theorem, or is it IVT, intermediate value theorem? If it asked me that such that r of t equals 0, that would be intermediate value. They're asking me about r prime. So first, let's see if this works or not. Are there any times that have the same y value? So let's see. Yes, on the ends, 9.6 and 9.6. If there were anything in the middle here that matched, that would be another indicator that yes. Okay, so the average rate of change from 0 to 24 is going to be 0. So I have to make sure that mean value theorem actually applies here. We're told that r is differentiable. Remember, the stipulations for mean value theorem is that r of t is differentiable. Therefore continuous on 0 to 24. So then I can say by MVT, by the mean value theorem, let's see. There is at least one time between 0 and 24 such that r prime of t is equal to r of 24 minus r of 0 over 24 minus 0, which is equal to 0. All right, last problem. On May 7th, 1992, the space shuttle Endeavour was launched for the purpose of which was to install a new pedigree kick motor in an there's some typos here. Communication satellite. The table provided by NASA gives the velocity data for the shuttle between liftoff and the jettisoning of the solid rocket boosters. Okay, so again, we have time, velocity. Use the data to estimate the height above the Earth's surface to the Space Shuttle Endeavour 62 seconds after liftoff. Use a left sum and a right sum. Why are they asking me about height if I have velocity? Because remember, when you integrate v of t dt, think about what those rectangles would be. They would have height of feet per second, and then you would be multiplying them by some width of seconds, and that's going to leave you with feet. So that's why I can figure out the height 62 seconds after liftoff. So where does the 62 go? We are saying accumulate this in the first however many seconds. So the left sum would be the integral from 0 to 62 of v of t dt is approximately equal to. This does not tell me what subintervals to use, so I'm going to assume that we are going by the table, I guess, like 0 to 10, then to 15, then 20. I think we're doing each of these. It's kind of annoying. Okay, so a left sum means start here, and you're doing the first number in each subinterval. So if I'm graphing these, you can graph them if you want to. We've got something like this, so we're doing first one, second one, third one. Okay, so the only one that's not going to show up is this one. So this is going to be 0. Oh, sorry. They don't all have the same width. So 10 times 0 plus, this is a difference of 5. 5 times 185 plus another difference of, where am I? 5, 319. I need to write these down, sorry. So I know what I've done already. Plus another difference. This is a difference of 12. And I would use 447. From 59 to 32, that's 27. And we're at 742. This difference is 3. And we would use 1,325. And my last distance minus 62 is 63 times, wait, right? 63? Yeah, I think so. Times 1445. Again, without a calculator, I would not be expected to do all of this math, so I'm just going to leave it like that. My height should be, or my label should be feet. All right, and then what about the right sum? So same idea, except you should include this one, and you should not include 0, 0. Meaning include means like in the heights. So you're still going from 0 to 10. That's a width of 10. But you're using 185 as your first height. And then all of this is going to be the same. So I'm going to copy all that down. Because these widths are still the same, right? The next one would be from 10 to 15, and I'm using this one now instead. Oh, wait, am I off by one? Hold on. Maybe I shouldn't just copy all this down. Okay, so on this one, I'm saying, like, here's my first one. From 0 to 10, I'm at 185. Check. And then from 10 to 15, that's 5. And now I'm at this height, which is 319. Oh, yeah, there we go. I was just copying these down. Sorry, it was just here to here. And the 5, I guess these widths are a little bit off because the 5, should that be 5, 185? No, that should be 10, 185 because it's 10 between here. So I should double check that. Okay, so then the next one, we did that. So then the next one is 5, and we're using 447. I'm used to the delta x being the same, and then you can just copy things down, but that's not the case here. So then we have a delta t of 12, and we're using this one, 742. And then we have a delta t of 27, and we should be using 1325. And then we have a delta t of 3, and we'd be 1445. And then we have a delta t of 63, and we should be using 4151. Still labeled in feet. All right, that finishes our Riemann sum problems. We're going to do abstract Riemann sums tomorrow. They are abstract, to say the least, so we will work on that and see how we do.